We've got 2 units left before your AP exam. Also a reminder, we got an email, Friday is the last day to pay for the test if you have not turned in your money for any AP exams. So, yeah. And there's not exemptions for an AP class, so you either take the AP exam or you take an equivalent AP exam from an older year. So, your choice. So Friday, money, if you haven't turned those in with, and I have extra envelopes if anybody needs them too. Yes. So hopefully you've had a chance to write. The SHM stands for simple harmonic motion, and we'll get to that definition as well. Let me scale this a little bit so you can see all the letters. And then we'll be doing waves and sounds. So we're going to have generic properties of waves, and if you've studied sinusoidal curves in pre-cal, is that pre-cal? You'll see some of that same type of motion come up in this chapter or section as well. And then we'll apply our generic information about waves to sound waves specifically. So today we're just going to do the periodic motion part. We'll relate it back a little bit to circles and kind of get a preview of some of the wave properties, but we won't spend too much time on that because I'm going to tie it in with the waves once we get to that section. But today we'll be talking about springs and pendulums, and we've actually had both of those things before. So you'll see a little bit later in your notes, it tells you to go back and review the work and energy chapter. So when you go to study for this next test, you may want to pull those notes back out as well, because you're going to see conservation of energy or elastic potential energy come up with the springs and the pendulums too. So I give you, hopefully you've had a chance to write down. Periodic motion is any motion that repeats in a regular cycle. And then a restoring force is a force that opposes the one that stretched or compressed it. And I think we had the restoring force before when we talked about Hooke's law. Do you remember studying the spring where you added masses to it? So the more mass you add, the more it stretches. Okay. The restoring force would be, you know how you stretch out your spring? The restoring force is the one that if you took those masses off, it's within the spring material itself, and it restores it to its original position. So it's going to oppose you stretching it, and it's going to make the spring compress back again. We'll also apply that to a pendulum. So if I pull a pendulum out, the restoring force would be the one that's going to make it swing and try to return back to that equilibrium position. Does everybody have a chance on this one? Good. Okay. I'm going to take off my shamrock. It keeps making noise and bothering me. Miss Jonte made me wear it because I didn't have green on. Okay, you can write while I'm talking. The simple harmonic motion, it's similar to the periodic motion. There is a regular cycle, but this one's a little bit more specific. And it's a back and forth motion that's caused by a force that's directly proportional to the displacement. And instead of, like we had Hooke's law before where we just stretched a spring in one direction, now what we're going to be doing is adding to that motion, and instead of just moving in one direction, we'll have a displacement or a motion that centers around an equilibrium position. So we'll have a spring that actually moves up and down instead of just being stretched down. And then we'll also turn the spring on its side, and it's going to go back and forth. So you'll get 2 directions of motion with the simple harmonic motion. And then the force being directly proportional to the displacement, that's still going to be the same. The more force you apply, the more it's going to stretch. We actually studied period with the circular motion. Remember, the period was the time to move once around a circle. It's the same type of idea, but now it's going to be the time needed for an object to complete one cycle of motion. So instead of our cycle being a circle, if we apply it to a spring, it's going to be the back and the forth. So if it's side to side, it'll be the left and the right, makes one cycle. If we have a spring bouncing up and down, it'll be an up and a down to be one cycle. When we apply that to a pendulum, we're going to pull our pendulum out to the side, and it'll be the time to swing across and back again. So we want 2 directions of motion, and the object returning back to its original position or as close to it as possible. And then amplitude is the maximum distance the object moves from equilibrium. So it's very similar when we did Hooke's law. It would be the amount of distance that got stretched. And I didn't put it up there, but period is measured in seconds. And you'll want your amplitude or I know it says X in parentheses. It can be an X or a Y, just X is kind of the generic symbol for the amplitude. But either way, it's going to be in meters. So when we do our lab today, we're going to work with springs, and you will want to convert your centimeters to meters. So make sure you do that when you get to your lab. This was the part, you already have this in your notes. There's nothing extra for you to write down. I just wanted to point out, remember to review in your notes Hooke's law and elastic potential energy. I'm also going to say conservation of energy, and we're going to have some practice problems to review those as well. So the elastic potential energy was the one that we applied to a spring, and we use spring as a generic term. That can be any material that stretches. It doesn't have to be physically an actual spring. But you need something that can be stretched out. Okay. And then it's going to compress backwards. So remember, for the periodic or the simple harmonic motion, we've got a back and a forth. So we've got a stretch and a compression. So you're going to have both directions of motion. That's what's going to be new. So we're not just stretching, you're stretching and compressing. And then, again, like we had before, that force is proportional to the amplitude or the displacement. And this one, you also have that picture in your notes, I believe. It's a review of the conservation of energy. This is just a reminder that your total energy stays the same, but it can change back and forth between potential and kinetic. And specifically, we'll have elastic potential energy. You can also have gravitational if you're moving up and down, but it applies side to side as well. And you can kind of see the background. It's faded out a little bit, but if we have a spring and we compress it, and then it's going to stretch, and then it's on its way to compressing, and then it stretches back out again. If you were to take a graph and graph that displacement over time, look at the nice curve you get. Okay, so that relates to the part that you've done in pre-cal with that nice even curve. And then if you want your calculators to practice, you're welcome to get those out. We'll go through these together. The first example problem is just going to review Hooke's law. So in case you didn't remember what that is, we're going to go through it together. And then we're going to have a conservation of energy problem. And then we'll be adding 2 new things that we have not done before. So we're in the review part right now. And I'm assuming that you remember Hooke's law, but just let me take a minute and kind of go back over that a little bit. The formula for Hooke's law was the one that looked like that. The force is the spring constant times the displacement. And there's a little s for spring force. You don't have to specify that because all of our forces are going to be spring forces. When we studied Hooke's law before, we actually put a negative sign in there to let us know that the restoring force and the displacement were in opposite directions. But since we're going to have that up and down motion, we're really only interested in the absolute value, so you're not going to see the negative sign come up, so don't worry about the negative part. And this K value, if you don't remember from before, that was called the spring constant. And it was a property that described the material in terms of its elasticity. So how easily does your material stretch? Okay. If it was a really high number, then it was more stiff and it was difficult to stretch it out. If it's a lower number, it's very flexible and it's easy to stretch. So just kind of a little bit of review on spring constant when I say those terms again. So what we've done in the past is use our force and how much it stretches to determine the spring constant. So we're going to do that first, and then the second part of the problem, we're going to rotate the spring on its side and see how we can use those numbers. So in the beginning, you're given a load of 50 newtons, so that's going to be our force. And then we need to know what the spring constant is, because there's nothing that describes the actual spring, so we're going to try to figure out what K is. And when we hang those 50 newtons from our spring vertically, the spring naturally stretches out 5 centimeters. And you do want to change that to meters. So I'm going to say 0.05 over here. And make sure that that's in meters. Can you do the math in your head? I double checked on the calculator too. So we're trying to figure out the spring constant because we're going to need it to know how much force we're going to have to apply to stretch our spring in a different way. So hopefully you were able to find out that our spring constant is 1,000. And then when we divided, we had newtons over meters. And newtons over meters is the accepted value. So when you do your lab today, make sure that you convert your kilograms to newtons to get a weight and not just a mass. And then you convert your centimeters to meters. So don't forget that when you do your lab. So now we have a way to describe the spring itself. And 1,000 is a pretty big number. So this is sort of a stiff spring. It's really hard to stretch it. And now we're going to turn the spring on its side. So we're going to place it horizontally. So that's what's new for this chapter. Now we're interested in finding the force. Does the elasticity of the spring change just because you turn it on its side? No. Okay. So we're going to keep K the same. And when we turn it on its side horizontally, we want to know how much force we're going to need to stretch it this new amount of 11 centimeters. So we're going to say the force equals, the spring constant stays the same. Okay. The actual material doesn't change just because you rotate it. And then 11 centimeters, how many meters is that? Good. Okay. So don't forget, you do want to convert. And then our meters are going to cancel. And you should get a force of 110. You could probably do that without a calculator, but I typed it in anyway. So the reviewing part that you've had before was the Hooke's law to find the spring constant. Now we're going to take that idea, rotate your spring around, place it somehow differently, and figure out what the force is needed. So that's the new section. Anybody still need that one? Our next one is going to go over conservation of energy. So this time you've got a slingshot. And you remember developing those labs where you wrote them and you designed stuff to talk about springs and energy? Some of you guys did a slingshot. Okay, I think 2 groups in here did. And it's the same kind of idea. We're just going to have a couple of steps. So we've got a slingshot consisting of a light leather cup, and it's got a stone. And it says you've got 2 rubber bands. We're just going to treat that as one object. So don't worry about multiplying or dividing by 2 or taking into account that there's 2 rubber bands. It's just going to be one object. So we treat that as one spring. It takes a force of 30 newtons to stretch the bands 1 centimeter. Okay. We're asked to find the potential energy, but we need to know what the spring constant is first. So that's probably going to be the first thing that you'll do whenever you're dealing with something that's going to stretch. So let's find our spring constant. Okay. So we're still using F equals Kx. So we were told that it takes 30 newtons to stretch the bands 1 centimeter. So make sure you change that to meters. And that should give us 3,000. Just double check. And now we can use that number. Anybody happen to remember a formula for potential energy of a spring? Elastic potential energy? It is. It is. Good. Okay. I used a U. You can do PE if you prefer. Okay. On that formulas page, there's a U for potential energy, but we also did PE. Okay. What? I don't know what that meant. Okay. So in part A, it wants to know the potential energy stored when a 50-gram stone is placed in the cup and pulled back 0.2 meters. So we're looking for the U value, the potential energy. We have our K, so we know that it's 3,000 newtons for every meter for this particular spring. And then we've got a new distance. So this time we're stretching at 0.2 meters. And you do want to square that amplitude. So we'll type that in. And you should get about 60. Do you remember the units for energy? Okay, good. And with what speed does it leave the slingshot? Now we're going to use conservation of energy for part B. And they actually gave us the information early with the mass of the stone, but we're going to need that for this section. So let me get part B. We're going to say conservation of energy. So we're going to pull the slingshot back. What kind of energy does it have? Potential. Okay. And it has elastic potential energy, which is the one we found in part A. Okay. So we're going to start out with all elastic potential energy. Is there any kinetic before you let go? Okay, no. So you can write +0. I'm just going to go ahead and say equals. And then after we let it go, what kinds it have? Kinetic. So all of that elastic potential energy is going to turn into all kinetic energy. Okay. Do you remember the formula for kinetic energy? Perfect. I'm just going to put that over to the side for you guys. So that's going to mean that all of our potential energy, the 60 joules, is going to be equal to half. They gave us a mass. How many kilograms should that be? Here. Yeah, good. So make sure you convert grams to kilograms. So 0.05 kilograms. And then we're looking for the speed, the v squared. So we'll take 60 times 2, divide it by our mass, and then you want to take the square root. You should get about 49. So both of those are review. You're still going to need to know Hooke's law and conservation of energy and elastic potential energy for the upcoming chapter. Okay. Does anybody have questions on that example? The next couple of slides are more just for your information. We're not going to test specifically over them, but I'm just going to mention a couple of things as we go through. So the springs, remember we talked about if you watch the up and down motion and were to graph that over time, you get that nice sinusoidal curve. Okay. They're going to be like waves and circles, and we'll come back and revisit the waves part when we study that a little bit in more detail. But this section, I went ahead and included it in here so that you can kind of see different parts of the wave labeled, like the amplitude, how high is it compressed or stretched, up and down. And then the period would be the time for an up and a down to complete that full cycle. This tells you a little bit about the period. There's an example problem in there. We are going to come back and see this when we get to waves. I just want you to know that that's in your notes. This new word called frequency, so that's in your notes as well, and we will come back and talk about frequency. Period is the time it takes to complete a cycle, and then frequency is the opposite. How many cycles can you get in a certain amount of time? But we're going to come back. And then the way that it relates to uniform circular motion, I just put that in there since we finished that chapter pretty recently, completely just for your information. Walked you through a couple of steps with some pictures. Derived a formula, completely up to you if you're interested in how formulas come about. I don't care as long as you get to the end and you know what the formula is. So next, this is the important part. Okay. So as long as you know what the formula is for period of a spring, I'm happy. The other part I included in there for you, for those of you that kind of want to make those connections and it's easier for you to remember and understand why. So, and remember it's going to be seconds. We're going to have some sort of mass hanging on a spring. In your lab today, we're going to use those cars on the tracks back and forth, and we're going to incline it and tilt it. So the car is going to be hanging on a spring and kind of moving back and forth, up and down a little bit. And in the formula, the M refers to the mass. So for you guys, it'll be the mass of your car, and then K is the spring constant. And on our example problem, we're given a mass. Okay. And it tells you what the period is and the total energy, and then we're asked to find the spring constant and the amplitude. So first, I'm going to have you scratch this out. I should probably do that in white. Instead of saying force constant, just to be more consistent with our words, just say spring constant. So part A, we actually are interested in the spring constant of the spring. Before we used the force in Hooke's law to find our spring constant, but we don't really have a force here, so we have to figure out some other way to find it. We're given a mass and a time, so that means we can use the period formula to find the spring constant. So I'm going to use the formula up above. I won't rewrite it. We're given the period of 0.25 seconds, and that's equal to 2 pi times the square root. Our mass was in grams, so we want to change that to kilograms. And the spring constant, or that elasticity, is what we're solving for. How do you get rid of the radical?
Square.
Good. So you want to square that. So I'm going to give you a little bit of time, and algebraically, if you have some trouble, let me know, and I'll come help you. Double check something real quick. You should get somewhere around 126, 127, depending on your sig figs. Anybody else need help with that? That should be the only thing you have to really look out for, is using your parentheses when you divide by 2 pi. Okay. Should get somewhere around 126. And then for part B, we're looking for the amplitude. Now we can use Hooke's law. Okay. I did not do that right. Hang on. We can't. I was still on the other problem, sorry. They're giving you the energy of the system, not the force. My bad. So we need to use potential energy, okay, to find the amplitude. So our potential energy is 1/2 kx squared. Okay. So we're going to say 2 joules. There's a point there. 2 joules equals 1/2. Plug in your K. And then x squared, and you're solving for x, okay, when they ask you for the amplitude. You should get about 0.18. So somewhere around 18 centimeters. Anybody need help with part B? So this is the new type of problem you would have that involves the period. Okay. Make sure that you're comfortable rearranging that formula to solve for mass or the spring constant, so it won't always be the period that you solve for. Can I go on? Okay, 2 more slides. I don't know why it's so hot in here and I don't have control over that. Okay, for our last section, okay, we are going to do this last page. We've got a pendulum now, so we're still going to look at the same idea of that rhythmic motion with our restoring force and the period, but apply it to a pendulum. So what forces act on a pendulum? Gravity and what's it hang from? Yeah. So we've got it hanging from a string, so that's going to be tension. I know that's going to disappear. I don't know why it's white. I didn't pick a very good color. Okay. So gravity and, oh yay, okay, gravity and tension. Free body diagrams are still really helpful. So even though we're not specifically on the forces chapter, I would look at drawing a free body diagram. So I have a pendulum for you over here. Gravity is going to point straight down. And our tension will point along the string. And I don't remember if you can recall about adding our vectors together. We had shifted those around and done a head-to-tail method. You can also complete the parallelogram. So I'm going to switch colors real quick. If we do that, I would draw a dotted line that's parallel to gravity and one that's parallel to the tension, and then draw a force that connects to the opposite corner of that parallelogram. And notice if you pull a pendulum back and let go, where that resultant force was that we drew, combining those, that's the direction of the path it's going to travel. This, when it says the vector sum of these forces is, that's the restoring force. And then we also have a period of a pendulum formula. It's really similar. It's still going to be 2 pi times the square root of some fraction. But now this up here, that's the length So the length of your pendulum, and then the G will be gravity. So 9.8 unless you're told otherwise. Okay. And the whole thing will still be measured in seconds. It's a type of time. Okay. It's specifically the time to swing across and back again. Today we're going to do a lab on the springs, and next class we'll do a lab on the pendulum. And then I asked you a little question down there. Does the period depend on the mass for the pendulum? Is mass anywhere in the formula? No. Was mass a part of the spring period? Yes. So you might have questions that come up on your next test that ask you to compare and contrast period of a spring and period of a pendulum. Okay. So they have similar formats for the formulas. One depends on mass and one does not. Okay. So just kind of keep that in mind. And then one example problem for you. So this particular visitor goes to a lighthouse and wants to determine how tall the tower is. Most people would like just open it up and read the brochure, but not this person. They carry thread and a rock with them everywhere they go. And say, oh, I'm so science oriented. I'm going to make a pendulum and I'll derive stuff and I'll count. Anyway, so I don't know who writes these questions, but here we go. We've got a pendulum dropped down the middle and they say, hey, can you swing that for me? So somebody pulls it back and they swing and it goes across and it goes back, and that takes 9.4 seconds. The height of the tower is going to be the length of our pendulum. We're assuming they're on Earth. So when we set up our formula, okay, you still have yours written on your page, right? So you don't have to rewrite it. We're going to set up the period is 9.4. And that's going to equal 2 pi times the square root. L is our height. That's what we're looking for. And then gravity is 9.8. I did a capital L so you don't think it's a 1. And you're trying to find the length or the height of the pendulum. I'll walk around and help you, but you should get somewhere a little under 22 meters. And then I don't think it's in this spot, but somewhere in your notes, I think I typed in that link and there's a little code there if you wanted little simulations to kind of help you go over anything with the period of the pendulum that's there for you as well. So we'll end with that and I'll walk around, help anybody who needs it. For your lab,